Okay. So as usual, I'll discuss some of the theory first, then before proceeding uh, to look at some problems. Okay. So in week one, we uh, we basically saw the axiomatic foundations of uh, probabilities. In particular, we saw what we mean by a probability space. Okay. Uh, but we also saw some properties of probability spaces. Um, we saw that a probability space is like could be a discrete space, uh, could be discrete, it could be countable, or it could also be uncountable. And so the axiomatic foundation of probability is at the heart of that is what we call a sigma algebra, and you have a measure defined on this sigma algebra. So in some places, you may see the term sigma field used somewhere, but they mean the same. Uh, I think one term is a modern term, and the other is probably an older term. So I'll stick to the term sigma algebra. Um, so um, just recall a brief recall. So when we say a probability space, what we mean is a sample space omega, then a measure, then a sigma algebra defined on omega, which you can denote by, let's say, this, um, let's say by a script p, and of course you have the measure actually defined, which is PR. Of course, in order to be a probability space, uh, you need uh, you need this PR to be a non-negative measure, and PR of omega is equal to 1. So this is basically your measure. Now, and of course, P is a sigma algebra. Now, a couple of things uh, that we saw last time. One of them was as follows. So, if you have a set A, which is a countable union of sets AI in P. Now, if these AIs are disjoint, uh, if AI AJ is equal to phi, I not equal to j, then uh, the probability of A is uh, is the sum of the probabilities of AIs. Okay. Now, from basically this uh, from basically this uh, definition or from this axiom, we get this result, which is very important. If you have a collection of sets, let me just write it. Uh, if AIs are a collection of are a countable collection of sets where AIs each of these AIs are a measurable set, uh, and if it is a growing sequence, in other words, you have AI is contained in AI plus one, is contained in AI plus two, and so on. So when I use this symbol just means set inclusion. If I want the inclusion to be proper, that if I when I want it to indicate that it is a proper subset, then I will use this notation. Okay. Otherwise, this notation is going to mean just set inclusion. It could be proper inclusion or it may not be proper inclusion. So if we have a collection, a countable collection of sequence of sets like this, let's say starting from A1 up to so on, then of course, if I ask you the question, uh, will this sequence of sets actually converge? So in other words, will limit uh, I tending to infinity AI, will the collection of these sets belong to this sigma algebra? Uh, if I ask this question, uh, can anyone answer if this is uh, whether the answer is true or false to this? I do not see a response. Uh, this is a very, very fundamental result because almost all of smooth probability theory. I mean, if I mean a lot of in many cases we work with discrete probability spaces. This happens in a lot of places in computer science, especially when you're dealing with discrete algorithms, where the probability spaces are discrete probability spaces. And a lot of these discrete probability spaces, you do not have to worry with limits. But when you work with probability spaces which are over real numbers or over just in general, like general uncountable spaces, then limits are very important in probability. And so the question to this is yes. If we have an increasing sequence of sets like this, then if we take the limit of this sequence, the set that will be it is going to be contained in this sigma algebra, which is P, script P. And the reason why it will exist is basically as follows. So what we have to do is we have to kind of think of a diagram like this. So let's say you have a collection of sets, let's say A1, and then you have, let's say, a bigger collection, let's say A2, uh, and likewise, let's say you have these collections. So imagine sets like these, okay, and let's say plus one. So what you do is that you create a disjoint sequence of sets. So you define a set called delta I, when delta I is equal to AI plus 1 minus AI. Okay. So if you have a sequence of sets like this, now what happens is that so each of these sets AIs belong to the sigma algebra, and therefore this delta I also belongs to the sigma algebra. Okay. Now the union. Uh, okay, just to rewrite what is this. So what is this limit I tending to infinity AI? This is equal to the union of these AIs. I hope it's clear to you why this is the case. If it's not, you can stop me and I can explain it and explain in some detail. But otherwise, I assume that this is obvious to you. Okay. Now, if that is the case, now you can write this union I is equal to 1 to infinity AI to be equal to A1 union uh, A1 union this big union delta I, where I is equal to 1 to infinity. Okay. Now, each of these sets in this collection, so the sets A1, delta 1, and so on, are disjoint. Okay, uh, fine, the disjoint, but there are also sets of this sigma algebra. And so it's going to be closed under countable union. So because so that closure under countable union basically tells us that if we have a growing sequence of sets like these, then the limit of such a sequence will exist in the sigma algebra. So it's going to be a measurable set. Okay. And this is very important to us as some of the later examples that we see will illustrate. Okay. So now we have this result, uh, which is um, the limiting behavior of uh, let's just write this under quotations. Limiting behavior of increasing or we also see this decreasing sequence of sets. But because we're in the context of probability, I will use the term event. Okay. So this tells us that if this is, you can kind of note it down as a theorem. If if these AIs are an increasing sequence, uh, the an increasing sequence, then the probability of limit I tending to infinity AI, and there is a shorthand notation for this. The shorthand notation for this is often written in this way. So the probability of this is equal to the limit of probability of AIs. Okay, so the probability of a growing sequence of sets is just the limit of the probabilities of the sequence. Okay, and I'll write down the proof. Maybe the proof is obvious to you. Uh, so the proof is basically following from this result that this set AI is equal to A1 uh, union uh, these unions of delta I is equal to 1 to n equal to 2. Okay, and so because these sets are disjoint, so the probability of this collection is going to be equal to a sum. So this is equal to probability of A1 plus sum over of probability of delta I is equal to 1 to infinity. Now, of course, when we say the probability of this set is equal to the probability of some of these terms, then this follows from real analysis. That what do we mean by uh, that what do we mean by a convergent sum? So when we say that a sum is a convergent, a sum which consists of infinitely many terms, when we say that such a sum is convergent, then what we mean is basically as follows. We mean that the partial sums, that is, in other words, if I define something called uh, if I define something called let's say I define a term called qi, and I write this qi to be equal to probability of a1 plus sum over of uh, sum n equals to 1 to I, probability of delta n, then what this essentially means is that uh, these QIs actually converge to probability of this union. But if you notice carefully, what is this probability? So this probability is probability of uh, so because they're disjoint, you can write it as equal to A1 union delta 1 up to delta n, right? But this term is equal to, well, this term is exactly equal to AI. So effectively, what you get is that these uh, probabilities of AIs tend towards probability of the union. So this is a very important result uh, that you have to remember. Again, if you're dealing with finite probability spaces, then these results are trivial; they follow automatically. Uh, it's when we're dealing with uh, when the underlying measure space is not finite, that's when a lot of these things become important. Okay, so likewise, you also have a theorem for decreasing sequences, and that theorem is as follows: if you have a decreasing sequence like this, then we're going to denote the limit of this sequence in this way. So this is the limit I tending to infinity AI, and uh, this is again equal to intersection of these AIs. So I hope this part is clear to you why this is the case. This should be obvious. Now, again, you have a corresponding result uh, as the previous one, which says that the probability of this decreasing sequence of sets AI is again equal to limit I tending to infinity probability of AI. So in a sense, this result and this result are duals of each other. Okay, so it's good to also I mean both these are very important results. They have to be uh, like you have to know them very well. Okay, now if I hope this is clear. Uh, if this is clear, then I move to some other topics. Um, okay. One of the topics here is Bayes theorem. Um, so in order to define Bayes theorem, we need to know what we mean by conditional probability. Now, of course, like most of us would know conditional probability from basically undergraduate level stuff that we know. But uh, but let us see how that is connected to the axiomatic framework that we have for probability. Okay, So let's first look at the axiomatic stuff, and then we'll see how that is connected to what we basically say call conditional probability. So recall again. I mean, the probability space is will be denoted by this tuple. Uh, okay. Now, if I have a particular set B, let's say B is some set uh, which is in my sigma algebra. So basically, B is an event. Now, I consider another. Uh, so, so P is my collection of sets, which I call events. I define a new collection of events, which I call B uh, with a subscript of B. Okay. And so, what is this collection of events? So, this collection of events is basically as follows. Uh, it is A intersection B for A in C. Okay. So all the events that are there in my probability space, I intersect them with B. Okay. And I define this new collection called PB. Now, if I ask you a question, is this uh, is P B a sigma algebra? Yeah, can you answer this question? Anyone?
Yes.
Yeah. Can anyone say if this is a probability space? Is B, PV, PR? So essentially, what I have done is that I'm my universe is now B. My sigma algebra is now all the events intersected with B, and the measure that I'm using over here is just the same measure. So in other words, if I take any set E belonging to this PB, I define this new probability measure. Let's call this PR prime. I define PR prime of E to be simply equal to PR of E. Now, is this a measure? Is this a probability space? Well, it's not a probability space, right? It's not a probability space because in order for something to be a probability space, you want uh, the probability of the universe to be equal to 1. But the probability of the universe is equal. Just give me a moment. But the probability of this base space is equal to it may not be equal to 1. So PR of B may not be 1. Because it may not be equal to 1. Therefore, this is not a probability space. Okay. But if something is not equal to 1, well, we know how to regulate 1. So what we have to do is that uh, we simply have to take, we simply have to normalize. So instead, what we do is that if you now consider P of B, and if you define the measure in this way, if you define a tuple in this way, this is a probability space. Of course, you require that B should not be a null event. So probability of B must not be equal to 0. Should not be a null event. So okay. So this is clear why this is a probability space. Hopefully it's clear to you. If it's not clear to you, you can ask me. Okay. Now, no, so for starting from so starting with any probability system, which has non-zero probability, then we can define a new probability space in this space. Okay. Now the question is, uh, how is why do we even define a probability space in this way, or how is this useful to us? Okay. Now, of course, the way it's useful to us is in conditional probability. Um, so, so again, I mean, so probability is something that we see in the real life. Okay, all this measure theoretic related stuff that we are doing is it's nothing. It's just an underlying mathematical model to formalize and axiomatize all the things that we see. So we are basically in probability we are asking certain questions, but we need to be able to translate those questions into mathematical formalism. And the underlying measure space and all that are just a way to model this. Uh, it's a way to mathematically model all the questions that we're asking in probability, or basically the questions that are legal. The kind of questions that you can ask. Uh, under this mathematical framework. We spoke at length about this in the first session. So now, when we're dealing with conditional probability, we often ask this question that it is basically an aim cost prediction. So probability is about making predictions, and and conditional probability is about making a posteriori prediction. So it is asking questions like, uh, what can I what can I say about something, and what is the something under quotes if I have information of some other thing. Again, this is under quotes. So this is the kind of questions that we're asking in conditional probability. Now, what is this something? So in the language of probability, each of these somethings translates to an event. So let's say some event A, okay, and this some other thing also translates to some event B, okay. So in other words, we are asking, what can I say about A if I know B has occurred, okay. Now, now let's look at this a little bit diagrammatically. So let's say this was your entire event space. Let's call this omega. Okay. And you have some event which is B. Okay. Now, now A is some other event. Let's say an event like this. So now if so what do I say? So okay. So when I say uh, what can I say about A? So A is a set. A is not a point in omega. It's a set. So it's a set of points uh, which constitute that event. So when I say that what is the probability that A occurs, by that I mean that yeah, again that is like a semi-formal term. So when I say that something like A occurs, that really has no meaning in the formal context. But what this means is that uh, what is the probability? What is the probability of A intersection B given B? Okay, so it's basically asking this. And when when we're working with this kind of the underlying probability space or the underlying probability measure would be P, and then whatever the original probability was, divide that with P. So this is the triple that we're going to be working with. Now the question is why are we going to take the triple to be working with? This is because the universe is no longer omega. The universe is now B because it is given to me now that uh, that B has occurred. So if B has occurred, then then uh, every other event in the universe, if that has to occur, it can only occur if it intersects with B, right? So therefore, this P subscript B has all the events which intersects with B. Okay, the events which don't
Good evening.
intersect with B are not included in P intersects with B because they cannot occur. Okay, so essentially any event when A prime is some event where A prime does not intersect, so then it is a null set uh, in this uh, sigma algebra. So the probability of this A intersection with B now occurring is basically the measure of this quantity. So probability of A intersection B upon probability of B, or is the probability with which A intersection B can occur. Again, when I say can occur, this is not a formal term uh, given B. Okay. And this particular quantity uh, use a special symbol, we write it in this way. Again, basically following the formalism of, so basically using the same kind of notation as before. So this is the definition. Probability of A given B is equal to probability of A with respect to B for probability of B. Now, of course, you have probability of A given B and probability of B is equal to probability of A intersection B is equal to probability of B is equal to probability of B given A times probability of B. Okay, and this is your base curve. Again, A has to be an event which occurs with non-null probability for this to be defined. If A is an event which does not, which occurs with null, is basically a null event, occurs with zero probability, then this conditional probability doesn't make sense. In other words, a question like saying what is the probability that something will happen, even that given that this has happened, is meaningless if this given part, the ending part of that question, uh, is not supposed to happen or cannot happen. So this is the base theorem. Hopefully this is clear to you, and this will be used in many cases. Of course, this should be well familiar to everyone. Um, Now, if this is clear, um, let's look at uh, the definition of the next very important thing in probability theory, which is the definition of the random variable. um, right. So, let's say you have a probability space. This, uh,
I couldn't get the
The
point,
question
the
is,
significance of the base theorem.
hello.
Can you ask your question again? Can you ask your question again? Hello. If you can't ask the question, if there's something wrong with your mic, you can type it in chat also.
Actually, sir, I couldn't get the point about the significance of the Bayes theorem, where we can apply, where we can use it. Can you please
Okay.
clear?
Yes, yes, yes. Yeah. So, right. So Bayes theorem is all about these conditional probabilities. So, so Bayes theorem. So it's about asking what is the probability that you want to make a posteriori predictions. You want to say you want to ask something like, okay, if I know something, um then what is the chance that uh, that this is what is causing it to be? Okay. Um, um, so now what happens is that what Bayes theorem allows you to do is that oftentimes what happens is that one of these quantities is known to you. So probability of a given b maybe may actually be known to you. Okay, and uh, so you basically use a Bayes theorem um, to answer one conditional probability when you know one of the other conditional probabilities. This answer is a little bit vague. I understand that, but we will look at some examples in which it will be clear. We can look at some examples from the assignment itself, where it will become clear how a Bayes theorem is used. But if you want like some kind of really deep application of Bayes theorem, then essentially this entire area of learning, which is called Bayesian learning, is one example where it's a kind of parameterized, is kind of learning a parameterized model um, based on uh, based on this base theorem. So yeah, so essentially let me, okay, maybe I can divert a little bit and talk about, since you already asked this question. So just give me a moment. Okay. Perhaps you know a little bit about parameterized models, or maybe you know a little bit, maybe you've seen a little bit of learning. So, okay, let me just uh, let me give you like a very basic example. Okay. So let's say you have some data. Okay. Let's say you have a data which looks like this. Let's say you know that the mean of the data is 0, but you have some data. Sorry. Okay. So something resembling a bell curve. Okay. and you know that you want to fit a Gaussian to this data. Okay, so you want something like n0 comma sigma squared, which is a Gaussian. Now, of course, you do not know what is the appropriate sigma that you want to, let's say, uh, uh, you don't know what is the appropriate sigma. All right. So now let's say you are given a data set. Okay. A data set is like some collection of points. So you have some collection of points, x1 up to, let's say, some x capital N. Okay. And yeah, think of each of these points as being points on the real number. So this is a subset of one, just for simplicity. And what you want is this basically. So if you have a collection of these points, uh, you can predict the density with which this point occurs. Okay, so that would simply be if this is the your uh, if this symbol basically represents the probability density function of the Gaussian, which has the sigma square variance, you can do something like x1. Okay. And likewise, you can do something like you can compute a quantity like this, which is called this probability of D, uh, subject to this n0 comma sigma squared. And basically, if you assume that the sample that is given to you is independently and identically distributed, you can say that this is equal to product of probabilities of uh, of each of these. Actually, not probability. Probability is not the right term. It's a density, so it's I'm going to use small p probabilities of each of these xi's. Okay, where this pxi is just equal to 1 by root 2 pi sigma uh, e to the power x minus e to the power uh, minus x squared by 2 sigma squared. Okay. So let us say you have defined a quantity like this. Okay. Now the question is, you want to know what is the right value of sigma. So what is the right value of sigma that you should choose, which would be an appropriate model for the data. Okay. So now you are essentially asking a question like this: what is um, if I so sigma is an unknown. You don't know sigma. Okay. So you want to compute sorry, 1 second. Yeah, x square is equal to xi. Yeah, right. Thanks. Yeah. Uh, right. So you are asking a question that what is the probability that sigma was the right parameter for my model given that I have my data. Okay. Now, how do you answer this? This is tough to answer, right? So you basically have two. You kind of have two um, events. Okay. So one event is the data that is given to you. So this data is a collection of points. Okay. So let's say so yeah, this is an event. This D is itself an event, and the choice of sigma is also you can think of sigma as being uh, a random variable. Okay, so you can ask what is the probability that sigma uh, is the appropriate um, or rather, let us ask this question: what is this quantity? Okay. Now the question is, why am I even interested in this quantity? Well, if this quantity is maximum, let me write it down. If this quantity is maximum, is maximized, then so let's say I do something like soup of over all sigma that is possible, and I do probability of sigma given this data D. Okay, if this quantity is maximized, then the sigma for which this thing happens, so this, if we call this a sigma star, if sigma star is when this quantity gets maximized, I can say that sigma star is a good estimate for my model, right? So now, of course, computing this quantity for any arbitrary choice of sigma is going to be hard, but Bayes theorem allows you to do it in this way. You can write this as equal to probability of D given sigma times the probability of sigma by the probability of D. Okay, right? Now, what is this probability of D given sigma? Now, of course, this is what we are not really in probabilities. We are going to deal with basically in probability densities. So this is something uh, that's not actually introduced thus far. But these are not probabilities. So instead, you should write as what is the probability density of sigma given D, which is just this. So the Bayes theorem. So the Bayes theorem basically percolates to the density to densities as well. It's not just for events, but also comes down to densities of random variables. So you have this given p sigma, and then some probability of this data set. Okay. Now, of course, this is some quantity that you know. This is basically this quantity. You can plug this in. And P sigma is an a priori probability. We call this an a priori probability. So an a priori probability is some idea of probability that you have in your mind. So you think that, okay, sigma is something like this. So you can assume that, let's say your sigma is some uniformly distributed. So if you do not have any particular a priori probability, you assume it's uniformly distributed over some 0,1. Okay. So now you have this, you basically have P sigma D equals to P D given sigma times P sigma. Okay. And then this is PD terms. Now, of course, the problem that we over here is to maximize this sigma. So so in order to maximize the sigma, what you can do is you can take a derivative of this quantity, and then you can set it to 0 and then study where the maxima lies. So the problem then is the problem of then computing the sigma for which this term is maximized evolves to looking at amounts to studying the maxima of this term. Okay. Um, and this is one actual method uh, um, in which this in which you actually learn models. Okay. Uh, so this is one application where actually Bayes theorem is used. Um,
Okay, thank you, sir. Thank you very much.
Yeah, I do not understand why choose sigma follows u 0,1. Yeah, as I said, this is an a priori probability. So an a priori probability is that you have some initial assumption about sigma. Okay, you do not know sigma. See, you do not know what sigma is going to be. Your sigma is an initial choice of what sigma is, right? So if you do not have an initial, if you do not have an initial knowledge of what sigma is, you can think that sigma is uniformly distributed. Now, of course, it cannot be. Let's say you know that sigma lies within a particular bound. So this is just like, for example, I'm not saying that sigma has to be this. It could be any other a priori probability distribution. In fact, you can take sigma to be equal to some other Gaussian also. It depends. So you should just read of it this way: P d given sigma and P sigma. So this P sigma is some probability density which is known to us in advance. It's an a priori probability density. Okay. It's generally taken to be a uniform density. It could be different also. Hopefully this answers your question. Okay. With that said, we got into this example in which we introduced a lot of terms like density, random variable, etc. Okay. Now let us formally define a random variable. You're given a probability space omega p and let's say some pr. Okay. Okay. So when we say a random variable is basically a function. Let us first see the formal definition, and then we'll see how it's intuitively related to the theory of probability. So often we denote random variables by letters like x, y, z, and so on. So a random variable is actually a function x from this space to the real line. Okay, but it's not just any space. It's not just any function. It is a function which satisfies this property that if you have um, any interval, let's say a comma b in R, and you look at the inverse of this a comma b. So you take the inverse image. So you consider x inverse of a comma b. Then this has to be an event. So this has to be in P, and this is an event. If maybe some of you are familiar with measure theory, then we say that it is a measurable map. So random variable is a measurable function. Of course, the underlying measure on R is going to be the Borel the Borel sigma algebra. So X is a measurable map. Okay. In general, like from this definition only, it follows that if you give me um, any measurable subset of X, so if um, if C as a subset of R is measurable, then X inverse of C is an event, which is just saying it belongs to P. Okay. Just give me 1 minute. I'll be back in 1 minute. Okay. So if I ask the question, what is random about a random variable? Right. Um, Fair question to ask, right?
Sir, actually, it is the outcome of the events.
Yeah.
Outcome of an event. Say we
Yes.
toss a coin, then the head
Yeah.
and tails, and the number of the die. So these are the events actually. So I think, sir, the events cannot be of inter lie in the interval which belongs to R. I have a doubt.
Yeah.
These are the outcomes, integers actually outcomes.
Uh. So essentially, what is happening is that um, uh, you have you have some kind of a data. So the one way to intuitively think about it is that you have a data which is your underlying probability space. Okay, but the thing with that underlying probability space is that often you do not know anything about that underlying probability space. An example would be something like um, yeah. So an example could be something like this. So let's say um, uh, you have let's say 20 students in a class that you are teaching. Okay, and you have 20 students in a class, and and so each student has a certain ability to perform in that class and has a certain ability to get a certain score in a certain exam, let's say. Now, of course, you do not know, so you probably kind of model it like a probability distribution. Okay, so you kind of take each student and you think that okay, each student has a certain has a certain chance of getting a certain amount of marks, right? Now, of course, if I ask you a question like, okay, if you give them an exam of that batch of 20 students, and I ask you what is the mean you can expect not let's not use the word expect. So what is the mean of that of the total score of the students? So the mean score of basically all the students in the class, that is a random variable. So it is a measurement. You should think about it this way. When we say a measurable map, it is basically a measurement on an underlying probability space. Okay. The probability space in this case would be a product space. It would be the product of the probability spaces of all the 20 students in your batch. Okay. And then it depends on how each of how each of the terms in that product space is basically depending on how you have defined it. Okay. So you have an underlying probability space and you make a measurement. That measurement is a random variable. Let's take another example which is somewhat simpler to understand. Let's say you're tossing a coin. Okay. Let's say you have tossed a coin um for like 100 times. You're tossing a coin. Okay. So now if I ask you what are the number of heads that you what are the number of heads you will get if you toss a coin for 100 times? Okay. Let's write down this question. Uh, Given a coin. Is head or
Excuse me.
tails? Yeah,
Hello. I
yeah,
have a doubt. I have a doubt in measurable map.
yeah,
We have defined that if we have any interval a comma b in R or intervals of the form minus infinity to closed interval x.
yeah. It's a very good question. And the thing is that if you have any particular set, okay, which generates the sigma algebra. So the definition of a measurable map is if you are given two measure spaces, if you take any measurable set and if you invert that measurable set, you will get a measurable set back. Okay. Just like maybe if you've done some real analysis, you would know that if you give me an open set, and if I invert that open set under a continuous map, I get an open set. Okay. Similarly, for a measurable map, if I invert a measurable set, I get back a measurable set. Now, why I've written it in this way is because sets of this kind, A comma B, sets of this kind actually generate uh, BR. So the Borel sigma algebra on R is generated by sets of this kind. Uh, and that's why it suffices to say that if you take if you take an inverse under just sets of this kind, if this is an event, then it's going to be a measurable map. Like in some sense, this is not the definition. This is like a uh, this is like a corollary of the definition. But I used this as a definition because it's easier to explain with intervals than to say with, oh, if you give me any random looking set in B of R, then if I invert that, I'll get back an event. That's kind of harder to visualize. So that's the reason. Um, was it clear to you?
It's okay.
Um,
Can you
general,
explain how that open interval A comma B can be expressed as either a union or intersection of Borel sets? You said
okay.
all
Okay.
intervals
So let's say,
generate.
yeah, of course. So let's say you start off with some kind of set. Okay, let's say you start off with a set like this, minus infinity, comma A, so minus infinity, comma B, let's say. So let's say this is
Yes,
your favorite kind of sets. Okay.
yes,
Now what you
yes.
can do, yeah. So now what you can do is that from this kind of set, you can generate this kind of set, um, B dash. How? Well, you do it in this way. Let's say B dash is some number on the real line, and you choose a collection of Bn's which tend to B dash. So Bn is a set of numbers which tend to B dash from the left. So one way to denote it is this. Okay. So now if you take the countable union of these guys, Bn's. So let's say you can take this each Bn to be equal to B dash minus 1 by n. Okay.
Square
So
foot.
now if you
Square
take,
foot.
Mhm.
Mm.
So if you take the union of these guys, now you get this set. Okay. Now let's say, well, let's say you have a set like this, minus infinity. This is, let's say this is A, and let's say this is B. Now if you do minus infinity, comma B, minus infinity, um, comma A, that is equal to um, A comma B, right? Now you know that if you have a set of the form A comma B, you can get something of the form A comma C, right? By the above procedure. So that's how you basically do these things. And the thing with taking inverses is that, and this is something, this is a handy thing to remember, is that uh, if you have something like, let's say, x inverse of A union A prime, that is equal to x inverse of A union x inverse of A prime. Okay. And this is true for countable unions as well. In general, if you have like x inverse of a countable union of some sets Bn, then the union operator will commute with this x inverse operation. So this is equal to union of x inverse of Bn's. Okay. Another thing to sort of keep in mind is the same with intersections as well. So if you have x inverse of of intersections of bn's, then again this is this commutes with the operation. Okay, and this
I,
is true for not
I
just
think
finite but countable
it,
intersections as well. Yeah.
it is not true. One of them is not true, I think. That X inverse union Bn need not
Yeah.
be equal to union of X inverse Bn. I don't know.
Okay.
One of these two is wrong. Either it is not true for union or not true for
It's true
intersection.
for both of them actually.
True for both.
Um, yeah, it's actually true for both. And yeah, it's going to be true for both.
If we take element wise, if
Yeah,
we
yeah, you
take
can take element wise. Let us
okay,
just show this. Let's prove x union of Bn is equal to union of x inverse of Bn. Okay. Now let's say you take some element of this guy. Okay. So let's say belongs to this union. Okay. If x belongs to this union, then x must belong to some bj, right? If x
you take
belongs to this bj, then it is going
you
to be
take an
contained
element,
in this guy, right?
you take an
Uh,
element entire set X inverse union Bn, not only union Bn.
yeah. I mean, what are the okay, okay, sure. Okay. Let us break it down. So if we have x inverse of union of Bn, so let's say you take some element over here y. Okay. If you
Mhm.
have some element y over here, that is over here, then if you map y back, so if you do x of y, then x of y must belong
Belongs. Mhm.
to any of the one bj's, right?
Union Bn.
No, xy must belong to union of bn's. If you have xy that belong to union of bn's, it must belong to one of the bn's, right? So there exists some bj such that xy is contained in bj, right? So now if you invert this back, so if you do x inverse of bj, surely this y is contained in x inverse of bj. So this side of the this is proved. Now you have to prove this. This is also you can prove in a similar way. Okay, both of these are actually true. Um, it's clear, right? It is clear, right? Or or should I explain a little more?
So, okay, if it is true for both, it is true.
Yeah. Um, hmm. Okay. So, yeah. So this is a very important thing to remember. It's that uh, it's that so if you have any Borel set in R, you can always write this Borel set as a union of intersections. And so when you take the inverse of such a union of intersections, uh, it because x inverse, this x inverse operation commutes with the union and intersection operators, so you can just bring the union and intersection operators outside. Okay, so if you have a set which looks something like this, let's just take an example. You have a set which looks like a inverse, let's say a1 a2 a3 union b1 b2 b3, and if you do x inverse of this thing, uh, this will commute immediately and you will get this. And likewise, you will get this thing. So essentially what happens is that you can always, like one thing to note is that if your sigma algebra is generated by a particular set of sets. In other words, if let's say, let's say, um, let's say Bj for j belonging to some capital J generates my sigma algebra, then it suffices to show that then if you want to show that a particular map is a measurable map, it suffices to show that I can simply that if I take only sets of this intersect only sets of this collection, and if I show that the inverse images are measurable sets, it's sufficient for me to show that it is a measurable map. I do not have to show it for all the sets of the sigma algebra. Okay, which is a much harder task. This you do not know the full structure of the sigma algebra. To show that something is actually a sigma algebra is a very hard thing. To show that actually something is a measurable map is a very hard thing. So a simplification of the problem is that you take a collection of sets which generates that sigma algebra, and then you show that the inverse of those collection of sets are measurable, which is oftentimes a much simpler task to do. Okay. Uh, so yeah, so this is not the textbook definition of a measurable map, but this is a working definition. Okay. Hopefully it's clear. Okay, okay, okay. So now we're kind of running out of time. So now, of course, if you have a measurable map, basically you have a random variable. I'll try to use the word random variable instead of using measurable maps. We're not in the context of a measure theory course. So let's say you have a random variable. So then what happens is that um, you can um, you can define a measure on you can define a measure on BR, okay, as follows. If you take any set in BR, so you take any set of the real line, which is a measurable set, and you define a measure on that, which you can call mu subscript x, where mu subscript x of E is equal to probability of x inverse of E. So sometimes in the language of measure theory, it's called a pullback measure. But what this actually does is that you have some space, which is your underlying probability space, and you have a map to R. Now what you do is that if you give me, um, just give me a second. Yeah. So you can assign a, sorry. So you can assign a measure to this set A comma B. It could be anything. Does not have to be an interval. But you can assign a measure to it by considering the event which is x inverse of A comma B. So in other words, let us actually take a real example. Okay. The example that we're going to talk about. So let's say the example is as follows. Let's say n coins are tossed independently. Assume they're identical coins. Okay. We're making a measurement on this experiment, and the measurement is basically this. So x is the number of heads that we see. Okay. Okay. So if n coins are tossed independently, what is the what is the underlying probability space? So if for one coin, let's say the underlying probability space is this. It is age comma t, right? So for n coins, the underlying probability space is a product of these probability spaces. Okay. And you make this measurement x from the product of this space to a real number. Okay. Which is basically the number of heads that you see. So now if I ask the question, if I pick any measurable set of R, that is, let's say I pick some quantity, let's say I pick some 1 comma 10. And if I ask you what is the probability? So let's ask this question, what is the probability that x lies in 1 comma 10? So oftentimes we'll write it in this way, probability of, and these are a lot of alternate notations, probability of x probability of x belonging to 1 comma 10. Okay. Sometimes we can write it as just probability with a subscript x of 1 comma 10. Okay. Sometimes we may want to write it as this also, mu x of 1 comma 10. So this is just equal to so this is equal to the probability of the event where so it is some of omega. So omega is something that belongs to this set. So omega belongs to this Cartesian product such that x of omega is between 1 and 10. Okay. So what does each omega look like over here? So this is a Cartesian product of this set h comma t. So each omega is a word. So in general, the omegas look like something like this. It looks like something. Yeah, the total number of events in this. No, the total number of events is not 2 to the power n. Someone said the total number of events is 2 to the power n. The total number of events is not 2 to the power n. The total number of points is equal to 2 to the power n. The total number of events is the size of the power set of this set. So let me write it down. The total number of points, yeah, that is equal to 2 to the power n. The total number of events is the power set of this. Okay, you're dealing with discrete probability spaces. So in these discrete probability spaces, if we don't write explicitly what the sigma algebra is, then you have to take it for granted that the sigma algebra is the entire power set that is being considered. Okay. It's only relevant in these continuous probability spaces. It's not really relevant otherwise. So you're looking at the set of words. So a word would look something like alpha 1, alpha 2, up to let's say some alpha n. So this is a word. So word is a sequence, or it's like an, yeah, you can think of it as an ordered sequence where each alpha I is either head or tails. And for each point, when I say a point, I mean a word in this case. So for each such sequence alpha 1 to alpha n, you have a map x which operates on this word and assigns it the number of heads in that word. Okay, so this is the actual random variable at work over here. And of course, if these are identical points, then you know what the probability of this is going to be like. And we're going to talk about these distributions, these binomial distributions, exponential distributions. There are going to be a lot of these distributions which will come up in the upcoming classes. Okay. Um, okay. So hopefully it's clear what a random variable is. It is a measure on some underlying measure on some underlying space. Now, of course, now if you have a random variable x, of course, you may want to um, you're interested in computing all kinds of probabilities. Like what is the probability that x belongs to some e? Okay, let's write it in this way. You're interested in what is the probability of x belonging to some e, where this e um, is a Borel set. Okay, but of course, one thing we know that the set of these Borel sets are generated by sets of this kind, right? So it suffices for me to just know what is the probability that x belongs to this set, right? Because if I know this probability, I know this thing also in theory, not necessarily in practice, but in theory, I know this. Okay. So this particular probability is of special interest to us, and it is known as the CDF, or just sometimes known as the distribution function of x. So this is called the distribution of x. And is commonly denoted by f with a subscript of x. Okay. So I guess that brings us to the end of all the things I wanted to discuss today. Now we can look at some problems. Yeah, most of the problems that I've seen in the week's assignment are very routine problems, and should be doable to all of you. Okay. Okay. Before proceeding, let me just let me give you one important result. This is a very important. This is one very important thing to know. So if you have a random variable, given any random variable, x, say um, age from R to R is a continuous map. So if we now consider this random variable, which is x age on x, this is a random variable. In other words, let's say I have a map from omega to R, which is my random variable x, and I have some continuous map from R to R itself. So if I consider the composition age composed with x, or just this is actually a random variable. And the proof is basically this. So if you give me any if you give me any open set of R, you give me any open set of or if you give me any open interval of R, an open set of R would be some kind of a disjoint union of open intervals. So if you give me any open interval of R, then the inverse image of this open interval, so if I take some like a comma b, then if I take the inverse of this a comma b under H, that itself would also be an open set. Okay. And the inverse image of any open set or any open interval on R is also going to be a measurable set. So if I take the inverse of this thing, age of x inverse, that is equal to x in h inverse of some a comma b is going to be some open set. So it's going to be equal to some x inverse of some union of ai comma bi. So which is the inverse of this, and this is of course going to be a measurable set. So this is a measurable set, is an event. Okay, so yeah, so this is a very important point to remember, because you will see many problems and many applications where you are not just dealing with any random variable, but you are dealing with a function of random variables. And when you are given these functions of random variables, then you may be asked to compute what is the distribution function of a function of a random variable. So so essentially, we may be asked a question like, what is f of h of x uh, instead of f of x? Okay. Um, um, are there any particular questions in the assignment that you want me to help you solve? Otherwise, I see most of the questions are very routine.
In assignment one, I want to
Ah,
know whether the problem 5 is correct.
just give me a moment.
Assignment one, problem number 5. I don't want any solution.
Ah, ah,
Please
ah.
just check whether that any one of the options is correct.
Oh, I have to solve that now. That would be difficult for me to solve it right now.
Because e- exactly A,
Ah,
either A or B. Exactly either A or B. That means it is not both. That
that
is A.
hydraulic landing assemblies question is what you're asking, is it?
Yes.
Uh, Wait 1 second. Uh, well, I mean, the way you solve this is as follows. So you define an event A, where
Yes.
A is a defect in
Yes.
shaft, and you define B, which is bushings, defect in
Yes.
bushings.
Yes.
Okay. And now what is given to you is that A has a probability of 0.08, B
Mm,
has a probability of 0.06,
mm.
and
P
A
of A.
intersection B has a probability 0.02. Right.
Mm,
Now, what they're asking is that
mm,
the probability that the assembly has exactly one of the two types of defects. So essentially, they're asking you
mm.
what is the probability of A delta B? Okay, I mean this is called the symmetric difference.
Ye-
This stands for A minus B union B minus A. Okay.
mm. Yes.
Um, so this is equal to P of A minus B plus P of B minus A. Okay.
Mm. Right.
Now this should be now this should be routine, right? So this is
Now,
equal to
mm,
now this is equal to how much is this? This is equal to 0.06 this term, and this term is equal to 0.02. So it is equal to, sorry, 0.04. So this is equal to 0.1. So yeah,
is it
none of the options is correct.
okay?
Yeah, none of the options is correct.
Because the next problem is based on this. That problem also the answer is not one of the options. Problem number 6. So if we
Hmm.
give two
Uh,
such problems, it takes a lot of time for us.
I don't set problems, sir. The
No,
problems
no.
are set by the professor.
Okay, professor. Because two
Yeah, I
problems.
don't set any. The assignments that you see in the course, I don't set any of them. I don't set any of the lectures. I don't set any of the assignments. I don't have, my business is only with having a tutorial session. Okay. So please contact NPTEL, and yeah, you can CC me. This is my email ID. Yeah, you can CC me. Uh, I'll be, that's fine. Yeah, I don't set any questions. Yeah, okay.
Thank you.
Yeah. There's still about 10 minutes left, so maybe we can discuss something. So, yeah, this is a good question. We'll discuss this. Maybe in the process of it, we give out the answer, but I think it's important to discuss this. So we have one question in this assignment, which is this. Now it says you have a cumulative distribution function CDF, which is basically what we have defined thus far. That it is a probability of x being less than or equal to x. Now the question is the CDF function continuous? Is the question. Can anyone answer this question? Is the CDF function continuous?
Continuous from the right, but not continuous from the left.
Yeah, it's continuous from the right, but it's not continuous from the left. What does this mean? So it means that so let's say x is my random variable and fx is my CDF. So it means that if I have a sequence of numbers xn which tend to x from the left, in other words, xn tends to x from the left, then fx, or rather limit n tending to infinity f of xn may not equal f of x. However, if xn is a set of events which is a set of points which tend to x from the right, then this is true. So this is the definition of left continuity. If this were equal, we'd say it was left continuous. If this is always the case, this is why it's right continuous. Now the question is,
So assignment
yes,
week 2, assignment number 6. Week 2, question
uh,
number 6.
yes,
Yes. Sir,
just let me.
can you please provide a hints to find how many distinct sets of the form X inverse
Absolutely.
of the Borel sigma algebra?
Okay, okay. Oh, okay. How many distinct sets of the form x inverse of b are there? Hmm. Okay. Yeah, I mean, okay. So if you do, so let's say BR is my Borel sigma algebra, and I do x inverse of BR. Okay. So this is So this is a subset of my power set. So you have to evaluate. So you have to basically consider the power set. Power set would be like pi, omega 1, omega 2, omega 3, and so on. So you consider the power set. The power set has 8 elements in it. And in that power set, you check which of the sets you check which of the sets can be an actual you check which of the sets can be an actual inverse image, right? So for instance, let's say omega 1. Is omega 1 the inverse image of a Borel set? The answer is yes. Why? Because omega 1 is equal to x inverse of 1. Is 1 a Borel set? Is 1 a Borel set? Good question, right? Is 1 a Borel set? Can you answer this question? No, please don't give out answers in the chat. Yeah, 1 is
I
a
have
Borel
not
set.
clear about the concept. I have not clear
So,
about the concept this.
okay. So what are you not clear about? Do you understand Borel sets or not? If you don't understand Borel sets or not, uh, I encourage you to look at the first session that we have, and we actually go through the course lectures of this course, which is given by the professor. And um, yeah, I mean, you'll have to go back to week 1 and clear out your concepts there. Like like if these are terms that are something that you've never heard, you've never come across, then it'll take some time to settle in. Okay. Um,
Okay,
okay.
sir. Actually, I didn't attend the. I cannot attend the first class, first session of your class.
The first session has been uploaded to YouTube. Um, so just give me a second. I mean, you have to. I'll give you the link to my YouTube channel.
This is my first class actually.
Okay. I'll give you the link to my YouTube channel. Uh,
Okay, thank you very much, sir. Thank you very much.
yeah, yeah. All sessions will be uploaded to this channel. Um, yeah, I mean, essentially, you evaluate all of these sets. So just to give like a example, omega 1, omega 2 is not going to be a set that is going to be included in this collection. Why? Because if omega 1 and omega 2 is a set which is included in this collection, then such a set, so let's say uh, x inverse of some b is equal to omega 1, omega 2. Okay. Then such a b must necessarily contain uh, such a B must necessarily contain 2, right? But if 2 is contained, then then X inverse of B will never just have omega 1, omega 2, but will also have omega 1, omega 2, and omega 3. Okay. So omega 1, omega 2, and omega 1, omega 3 are invalid. They will not belong to this collection. Okay. So this is how you basically have to solve this. Yeah. um, yeah. So going back to this problem, um, I'll give you a hint. Okay. The hint is basically as follows. So if probability of x uh, if probability of x belonging to minus infinity comma x open interval is equal to probability of x belonging to minus infinity comma x closed interval, then fx is continuous at x. Yeah, then fx is continuous at x. uh, you should try to prove this result. Okay, you should try to prove this result. This is a homework. Okay, I guess that brings us to the end of today's session. If you have any questions, I can wait for 2 minutes more, 2 to 3 minutes more, and then we can end the session.
Okay, thank you.
Okay.